In the last video, we saw that Cardan introduced complex numbers in the year 1545 in his book Ars Magna. This is the front page of that book. Right now, we would like to know that how he came across such numbers, what he was exactly doing when he saw numbers which are actually square root of negative numbers, right? Which we call as complex numbers. So let us see what he was doing. He was actually whenever you you take any textbook on complex analysis, you will come across this thing that numbers appeared when people try to solve these quadratic equations. So let's see what is the story, right? So suppose you have this quadratic equation and you want to solve this quadratic equation. So we have this formula for solving this quadratic equation, and this formula is very old. Some 2000 years BC, there was a technique which is equivalent to this formula, right, for solving such quadratic equation, right? So Cardan was actually using this formula for solving these equations, and then he saw, what if this m square plus 4c, this m square plus 4c, which appears inside the square root, is negative, right? He was solving some equation and he saw that in his equation m square plus 4c was negative. So he was like, okay, what is this minus 2, square root of minus 2 or something like that he came across, and he was like, okay, what is this? I know there is no number whose square is negative, right? So he knew that x square is equal to minus 2. No such number exists, no such real number exists. So x is equal to square root of minus 2. So he was like, it baffled him that what is this, right? So so that is the first time that Cardan saw this square root of negative numbers, right? But then he discarded, like, in his book he said these are actually useless numbers, we actually don't need these numbers, right? Why he discarded? So it is not that he didn't have that imagination, he didn't have that power of imagination to digest these numbers, but it was because at that time everything mathematical was connected to geometry. So basically solving this equation x square is equal to mx plus c was equivalent to solving this geometrical problem. What is that geometrical problem? This geometrical problem is that you have a parabola y is equal to x square and you have a straight line y is equal to mx plus c. Now suppose I want to find out the points of intersection of this parabola and this line, then what I have to do, this is y is equal to x square and y is equal to mx plus c. So basically I have to find x such that x square is equal to mx plus c. So basically I want this point. At this point this equation is satisfied as well as this equation is satisfied, and at this point this equation is satisfied as well as this equation is satisfied. So I have y is equal to x square and y is equal to mx plus c for these 2 points. So basically I can equate x square is equal to mx plus c. So when it was the time of Cardan, so this was not thought of as a problem in itself, but it was a problem of this geometrical interpretation. So basically we were not we didn't want to find the numbers which are solving this equation, but we actually wanted to find out these points, right? So when Cardan was solving the equation where m square plus 4c was negative, what that physically represented was, I will show you in the next slide. So basically we had this problem that we have a parabola, we have a parabola y is equal to x square, we have a line and we want to find out the points of intersection. So when this is the case, when L1 actually intersects the parabola, then that m square plus 4c which appears in that formula is actually positive, right? And when m square plus 4c is less than 0, this is the case that in that case actually this line doesn't intersect this parabola at all, right? Okay, so Cardan he saw that, okay, this is a line and this is a parabola, so m square plus 4c, whenever this is negative, and that means whenever in this formula square root of negative numbers appeared, that is actually useless case because there are no physical points at that time, right? So that's why he discarded complex numbers, right? That's why he didn't pursue with complex numbers. That's why in his book Ars Magna he said, okay, these are useless because anyway they appeared when I am solving this problem. I want to know that where this parabola and this line intersect, and these two geometrical figures, they don't intersect at all. So it means that and they are compatible. Then if the some unusual quantity is appearing in this formula, that is because that is an imaginary quantity, because there are no points which no points common to this parabola and the straight line. So that's why he discarded these complex numbers. So basically this is not the quadratic equation we were solving which leads to the this complex numbers. The obviously complex numbers appeared when we were solving quadratic equations, but they were rejected because there was no geometrical interpretation that for the fact that these numbers should exist, right? So basically, so it was not actually the quadratic equation that forced complex numbers to be taken seriously. Of course, first time complex numbers appeared when we were solving quadratic equations, but soon after seeing such numbers, they were discarded because there was no geometrical interpretation. It was actually the cubic equations, right, that led uh, to the subject of complex numbers. How? Okay, let's see. Suppose you consider this cubic equation, cube is equal to 3px plus 2q, and you can note that you have any cubic equation, you can always reduce that cubic equation to this form, right? So basically what this represents geometrically, this equation represents that you have a this 3D thing, y is equal to x cube. This is the curve of y is equal to x cube, and you have a straight line, y is equal to 3px plus 2q. So no matter what, how this straight line looks like, for example, this will go infinitely there and upside also, right? So all the lines, you always have an intersecting point of a line and this cube big curve, right? So for example, it is not the case, for example, in last case we had a parabola and a line that these two quantities did not intersect at all, but we cannot have a situation here, right? Because this will go infinitely up down. So whatever is the line, you will always get an intersecting point, right? Okay, so this equation always has a solution. It always has a solution, right? Okay. Okay, so for this particular equation, Cardan, he gave this formula. He said that this equation can be solved with this formula, right? Obviously, we can derive this formula, but that is not our aim right now, right? Okay, so he gave this formula, and after that, for 30 years, almost 30 years, nothing happened. But after 30 years, this Bambelli, he was solving this equation. He was solving this equation, and he used this formula given by Cardan in his book, this Lie algebra. This is the book where he was solving this equation, right? You can compare this equation with this equation, and you will see 3p is equal to 15. So your p is actually 5, and your 2q is equal to 4. So your q is 2, right? So he was trying to solve this equation using this formula. So you substitute this p is equal to 5 and q is equal to 2 in this double star formula. You will get x is equal to cube root of 2 plus square root of minus 121 and cube root of 2 minus square root of minus 121. So he saw this negative numbers, right? Square root of negative numbers. He saw these negative numbers inside the square root sign again, right? First time we discarded because geometrically we saw, okay, they are useless, right? But now he knew that this equation has a solution, and he actually found that solution. You can see that x is equal, he knew that x is equal to 4 is the solution, because if you say 4 cube is 64 and 15 times 4 plus 4 is 64, so obviously 64 is the 4 is the solution. So he knew that there is a solution, real solution for this equation, but in the method given by Cardan, right, these square roots of negative numbers were appearing, right? But he cannot ignore now. He could not ignore these numbers because he actually knew that the solution exists, right? So he had a thought in his mind, okay? He had this thought, and he called it as a wild thought, right? What he thought, okay, he got this x is equal to this. This is from Cardan's formula he got, right? He thought, what if this quantity is 2 plus something and this quantity is 2 minus the same something, right? He said, okay, if this is the case, then this plus this will give him 4. Okay. and he knew that 4 is the answer. So he thought, okay, I want something such that this is equal to 2 plus something and this is equal to 2 minus something, so that he can add these two quantities to get his 4, right? So what he did, he started with this square root of minus 121. So he wrote it like square root of 121 times minus 1. There is no problem here. So 11 square is 121 times minus 1, and 11 will come out of the square root. So he get 120 square root of minus 121 as 11 times square root of minus 1. So he wrote x as cube root of 2 plus 11. He replaced this thing with 11 times square root of minus 1 plus cube root of 2 minus 11 times square root of minus 1, right? Okay, so he got his x as this thing plus this thing. Okay. Now he did some thought process, some deep thinking, and then he came out with this thing: 2 plus square root of minus 1 raised to power 3. He used this formula: a plus b cube is a cube plus 3a square b plus 3ab square plus b cube, right? He used this formula. So he had 2 cube a cube plus b cube plus 3a square b plus 3ab square. So this is 2 cube is 8. Now square root of minus 1 cube is actually square root of minus 1 times square root of minus 1. So this will be square root and square will cancel. So it is minus 1 times square root of minus 1. So it is minus 1 times square root of minus 1. So this is 4 into 3, 12 square root of minus 1, and square root of minus 1 is again minus 1. So it is 3 into 2 into minus 1, that is minus 6. So he got it as 2 plus 11 square root of minus 1. Okay, this cube is this thing. And then he took the cube root on both sides. He got 2 plus square root of minus 1 is equal to cube root of 2 plus 11 square root of minus 1. So he saw that this quantity is actually equals to 2 plus square root of minus 1. And similarly, you can see that this quantity is equal to 2 minus square root of minus 1. So then he added these two quantities and he cancelled these two terms and he got 4, right? This is what he did in his book. But after doing all these things, he said, oh, what the hell I am doing? These numbers are useless. Okay, he actually saw a way. He saw a way to solve these equations, right? He knew that answer is x is equal to 4, and on the way he saw these complex numbers. Okay, this algebra, there is nothing wrong with this algebra. This is actually a beautiful thing. But that complex number, he could not digest that such numbers, they are there. Actually they are there, right? So he again rejected his theory, and then we know all the story that for 250 years nothing happened, right? Till Gauss introduced this geometrical interpretation, right? So this is how complex numbers appeared for the first time. Okay, thank you.